Hello, my name is Andrew Miller. I'm Chief Technical Officer of Thatcher Research, the UK Automotive Research Centre. In this briefing, I'll update you on the status of the development of vehicles towards becoming autonomous, driverless cars and the potential impact on insurers. So let's look at the landscape. For the past 100 years, innovation within the automotive sector has brought about major technological advances, leading to safer, cleaner and more affordable vehicles. Since Henry Ford introduced the moving assembly line, the changes have been evolutionary and have provided us with one of the most complex products in the world, affording us very high mobility. But we forget that the success of the automobile was not completely envisioned. Henry Ford once said, if I'd asked my customers what they wanted, they'd have said a faster horse. In other words, we don't know what we want until we have it. This is nowhere more true than with today's mobile telephones. And of course, anyone under the age of 25 does not say mobile, it's a phone. This is an important factor because one of the unforeseeable aspects of this whole driverless car revolution is the potential for the market to demand this technology faster than we in industry and the government and regulators can keep up with. Smart mobile phone growth has been staggering. In 2014, sales of smartphones worldwide topped 1.2 billion, which is up 28% from 2013. What could the future hold for driverless cars if we get a taste for the benefits they bring? Now, in the early decades of the 21st century, we're on the cusp of revolutionary change with potential to dramatically reshape not just vehicle manufacturing, but also the way we interact with vehicles and indeed the future design of roads and cities. And the timing may be sooner than you think, and it's possible that children born in the 2020s will always expect a car to drive itself. This could be normal. The tangible benefits are huge. New collision avoidance and intelligent vehicle technologies could deliver significant and cost-effective benefits to UK citizens and the UK economy. Thatcher Research estimates for autonomous emergency braking (AEB) show fatality reductions of 1,220 over 10 years and all casualty types to reduce by 135,000. Low-speed AEB is already showing benefits in reducing front-to-rear crashes, and claims data in the UK is showing a 20 to 30% reduction in resultant personal injury claims, and this is now reflected in premium reductions. The latest data is showing over 40% reductions in personal injury claims on the latest Golf variants fitted with the AEB technology. Currently, much of this technology is being driven by Euro NCAP. Euro NCAP is the European New Car Assessment Programme, which puts about 40 new vehicles through a series of severe crash tests and collision avoid assessments, the well-known star rating system. Thatcher Research is the UK insurer's representative in this organisation and has a fully Euro NCAP accredited test laboratory, the only one in the UK. On behalf of Thatcher, I'm currently chair of the board of Euro NCAP, which is reviewing future strategy for the inclusion of assessment tests for autonomous technology, so we can provide good information to consumers. More information on this can be found at www.euroncap.com. But, strong as they are, market forces, including consumer pressure through Euro NCAP, will not deliver change as fast as regulation could. It typically takes 10 to 15 years for a new technology to appear on the new car and LCV fleet, and a further 10 to 15 years to change the fleet through replacement. Thus, we believe that there is a role for government to incentivise the fitment of these new technologies. As most accidents are a result of human error, it is likely that these new driverless technologies will have a significant positive effect for the UK, with knock-on effects in healthcare, congestion and overall UK economic growth, and also contribute to further downward management of CO2. Thus, there is an urgent need to evaluate and quantify these benefits and to create a strategy to manage and or encourage their implementation. And Thatcher Research is putting significant resources towards this in future research programmes. European legislation is slow and lowest common denominator. We believe that the UK should set its own strategy and develop effective regulation and other interventions which will deliver what is good for the UK. And Thatcher's lobbying of government and evidence to the Transport Select Committee has made this point clear. The government at a national and local level has a responsibility to develop a long-term integrated road mobility strategy. And the government has now acted with recent publications from the Department for Transport laying out a clear pathway to create the right environment for this. Entitled The Pathway to Driverless Cars, Summary Report and Action Plan, This was accompanied by the Pathway to Driverless Cars, a detailed review of regulations for automated vehicle technologies. The review identified issues that need to be addressed to enable automated vehicle technology testing on UK roads whilst maintaining high levels of road safety. It covers the best and safest ways to trial vehicles where a qualified individual is present who is capable of taking control of the car. It also looks further ahead to the implications of potential use of fully autonomous vehicles. A further consultation has taken place with the research community to develop guidelines for the safe on-road testing of autonomous vehicles, and it is expected that this will be published in mid-2015. The current business incubation strategy is also well designed, and we look forward to the effect of the new Transport Catapult. This was set up to support business in the new technology areas by setting a strategy to encourage the development of a more technically sophisticated fleet on a fit-for-purpose road network, ensuring that both the UK car makers and the business sector around the operation of the UK fleet will be best placed to take advantage of the new technologies. So that's the landscape. Real opportunities await for the UK to benefit from autonomous vehicles, but the devil will be in the detail. Let's look at some of that now. Firstly, we'll look at autonomy and intelligence. The term autonomous means having the freedom to act independently, and it's this definition which we also use when referring to AEB systems which brake for you. When this term is applied to a car, we're referring to a decision taken by embedded intelligence in the car systems. Embedded intelligence is logic rules-based software, e.g. if the forward-looking camera image contains a predefined pixel pattern associated with the car and the radar confirms that a reflection pattern is similar to a predefined pattern associated with the car and the reflection times indicate that the driven vehicle will converge with the reflection within a certain time, then the emergency brakes will be applied. It's pure logic, not decisions taken by chance. This type of embedded intelligence is common in many mainly electronically controlled systems across a range of engineered objects, from central heating to automated trains. On this basis, we refer to driverless cars, the presumption being that the lack of a driver is because the car has embedded intelligence superior to that of a human driver. Embedded intelligence is not to be confused with artificial intelligence, which is usually defined as a machine which is a truly independent agent and which can, amongst other things, reason, problem solve, plan and learn. Researchers in the field are also considering other intelligence attributes as part of this emerging definition, areas such as perception and creativity. Recent leading scientists have spoken out against the creation of real AI as they believe that creating a more intelligent species might be an own goal. So back to cars. It may be that some manifestations of vehicle embedded intelligence will have a learning capability upon which the vehicle performance will depend in future, designing new rules. Some researchers posit that this capability may be a prerequisite for the embedded intelligence required to drive a vehicle due to the enormous numbers of logic rules which would otherwise have to be written. However, it is unlikely that this would be easy to manage within product or liability regulation, as it would be difficult to accurately identify and/or guarantee the vehicle's system performance at any time. So let's look at levels of autonomy. With each increasing level of autonomy, new driving tasks will be possible for the vehicle to control based on its embedded intelligence. The following figure shows this increase in level. The scale goes from 0 to 5. Level 0, no automation on the vehicle. Level 1, automated systems which assist the driver, such as adaptive cruise control, lane keeping assistance, blind spot warning and autonomous emergency braking. Level 2, partial automation. These systems control the vehicle in low speed situations such as parking and low speed traffic following. Level 3, conditional automation. These systems such as Super Cruise will be available from 2018 onwards and allow the driver to disengage from the controls, although crucially he/she must remain alert and attentive and be ready to take over the driving task quickly. Level 4, high automation. This is a vehicle which can negotiate complex driving situations but which does not require the driver to be ready to take over the controls quickly. Level 5, full automation. This is a vehicle which does not require any human intervention at any time. The occupants are passengers. There are significant technical challenges for engineers in the development of Level 4 and Level 5 vehicles. The road space is incredibly complex, with threats and hazards which test our fast human brain, our stereoscopic vision, attuned to notice change, and our relatively fast reactions. Programming a set of software rules to manage the driving task is very hard indeed. At present, many of the driverless car demonstration vehicles are packed with computers. This is because the computing power required for the complex task of assessing all risks and threats, designing a safe future path for the vehicle, has almost innumerable variables, each one generating computer work. Thus, the engineers talk about the technical leap from the simple systems which follow a lane marking or detect a human shape in a camera to one which can combine all the potential decisions into a vehicle's systems control, a huge task. However, Moore's law states that computing power doubles every 2 years, and this still holds true. In addition, research into neurocomputing will create further huge algorithmic efficiencies, further accelerating the power of the control systems to be able to manage the autonomous driving task. Thus, it is entirely plausible that the development of robust software rules and the development of ever more powerful computers will deliver the autonomous car in the timescales which the vehicle manufacturing industry is expecting. There are also new players entering the vehicle engineering arena, shaking up the existing car makers. The Google self-driving car is a project by Google that involves developing technology for autonomous cars, mainly electric cars. The software powering Google's car is called Google Chauffeur. Lettering on the side of each car identifies it as a self-driving car. The project is currently being led by Google engineer Sebastian Thrun, former director of the Stanford Artificial Intelligence Laboratory and co-inventor of Google Street View. Thrun's team at Stanford created the robotic vehicle Stanley, which won the 2005 DARPA Grand Challenge and its $2 million prize from the United States Department of Defense. In May 2014, Google presented a new concept for their driverless car that had neither steering wheel nor pedals, and unveiled a fully functioning prototype in December of that year that they are planning to test on San Francisco Bay Area roads in 2015. Google plans to make these cars available to the public in 2020. The Silicon Valley giant has been more recently followed by Apple, who are reported to be recruiting hundreds of staff to develop an electric car. Former employees of American car maker Tesla are among those who have recently joined the tech giant. Apple famously has an unrivaled ability to provide consumers with exactly what they want without them previously knowing that they wanted or needed it. The traditional car industry needs to take the news seriously, as Apple is currently in 2015 sitting on a cash pile of $150 billion, which is the amount greater than the combined market capitalization of Ford and General Motors. Lastly, Tesla. This new electric car startup has taken the automotive industry on at its zenith, building highly desirable executive cars with a proper range of over 200 miles. Not only has the company created great cars with a really powerful brand with an eco message, it has single-handedly made history through its use of over-the-air software updates to add functionality to its vehicles for its consumers, even on its fastest model removing 0.1 seconds from the 0 to 60 time. How's that for customer satisfaction? The digital innovators are there already. The vehicle manufacturing industry is getting there with the engineering. A brave man would bet against it. So let's now look at the stakeholder map. There are a wide range of affected stakeholders, and insurers are key. The societal risk of the use of vehicles is managed using a legal framework with agreed liabilities, and it's here that insurers can play their part in the development of the use of these vehicles. The following diagram shows the main stakeholders who will be actors. Government policymakers and wide societal stakeholders will have to understand the cost of benefits case and develop policy and regulation accordingly. The vehicle manufacturing industry, its suppliers and associations will have to develop interoperable technical standards at an industrial and regulatory level. The vehicle manufacturers will have to work with consumers and their associations to develop a good understanding and demand for the new technologies. Insurers, their associations and the financial regulators will have to work with vehicle manufacturers and their regulators to develop ways of supporting the introduction of the technologies through clarifying risk and liabilities. This is an immensely difficult area for insurers. They must be able to understand the risk clearly if they're to be able to quantify the premium correctly. For a driven vehicle, this is currently relatively straightforward. Thatcher Research currently provides detailed analysis of the risk associated with each car and publishes the risk on a number system from 1 to 50, the group ratings. We systematically analyse every new model and variant of it, starting with its value, the cost of 24 easily damaged components such as bumpers, doors, etc., the engine power and its 0 to 60 time, the results of a series of low-speed damage tests designed to comparatively analyse the model's propensity to be damaged, a physical security test to gauge its theft resistance, and lastly, if fitted with an ABS system, how well this avoids a crash at a range of speeds. This group rating system has been used for many years, and the output group rating numbers are used right across the UK insurance industry and are combined by insurers with the driver profile to create the overall risk profile for a given driver-vehicle combination. But with autonomous cars, we expect the driver to be less involved in the driving task, and thus we also expect the driver profile to play less of a part in future underwriting. The question of the part played by the vehicle is the moot point. We expect an autonomous vehicle to be inherently more competent than a human driver, but whether we find the vehicle's autonomous vehicle systems to be different between different models is the big unknown question. We see significant differences between them at a subsystem level, but whether this translates into differences between highly and fully autonomous vehicles remains to be seen. As you might imagine, this is a big area of the Thatcher Research's future focus. So let's look at road traffic regulation. In the UK, the 1988 Road Traffic Act regulates vehicles' use of the road, but does not state in specific terms that the driver must be in control. The UK Government, the Department of Transport, are in the process of reviewing the issue of control, a regulatory framework for testing, and the use of autonomous cars. Insurance liability, tax, MOT, driving licence and revamped highway code are all to be agreed by summer 2017. This follows on from the provision of funding in autumn 2014 to 4 cities, Bristol, Milton Keynes, Coventry and London, Greenwich, to pilot autonomous cars. However, this position contrasts with the 1968 Vienna Convention on Road Traffic. The article states every moving vehicle or combination of vehicles shall have a driver. In Article 13 of the Convention, every driver of a vehicle shall in all circumstances have his vehicle under control so as to be able to exercise due and proper care and to be able at all times be in a position to perform all manoeuvres required of him. A working party on road traffic safety in the UN ECE is developing a new clause referring to the technical regulations, as well as including a broad definition of driver assistance systems. In the USA, federal legislation lags behind, and we wait to see their future actions. Legislation has been passed in 4 US states and Washington, D.C., allowing driverless cars. The state of Nevada passed a law on June 29, 2011, permitting the operation of autonomous cars in Nevada after Google had been lobbying in that state for robotic car laws. Nevada's laws went into effect on March 1, 2012, and the Nevada Department of Motor Vehicles issued the first license for an autonomous car in May 2012, to a Toyota Prius modified with Google's experimental driverless technology. In April 2012, Florida became the second state to allow the testing of autonomous cars on public roads, and California became the third when Governor Jerry Brown signed their bill into law at Google HQ in Mountain View. In December 2013, Michigan became the fourth state to allow testing of driverless cars on public roads. And in July 2014, the city of Coeur d'Alene, Idaho, adopted a robotics ordinance that includes provisions to allow for self-driving cars. In Europe, a range of trials are being set up, but the UK is the only country which is encouraging open access to public roads under strict control conditions. Let's now look at product regulation. Product regulation in many countries does not allow highly or fully automated driving. Examples of specific regulations such as ECE R79, steering equipment, and ECE R48, lighting. These will have to be revised, and national regulations revised in turn where necessary. In the UK, the approach adopted by lawmakers has been one of gradual accommodation of new technologies, and the challenges presented to fully automated driving are unlikely to be any different. One of the challenges for the immediate future for an international vehicle manufacturer, component or technology supplier will be the variety of regulatory regimes adopted in different jurisdictions. So let's look at product and other liability. Early legal opinion, which is untested, is forming the view that existing product liability law can be applied to highly and fully automated driving, and it's not expected that a special liability law will be required. The Consumer Protection Act of 1987 provides a framework for redress where a defect exists within a car, placing liability on the producer. Vehicle manufacturers will have to review their insurance position very carefully, as there will be increasing focus on the provision of information and training to car purchasers users as to the level of automation in a particular product and what level of participation is required by the driver user. Greater level of after-sales care, technical updates and upgrades will have to be provided, and the gathering of a great deal of commercially valuable and personally sensitive data during the use of a fully automated car creates data protection risk. Test cases where accidents still occur may ultimately lead to industry agreements regarding apportionment of liability and the consideration of a no-fault compensation scheme, but outcomes in this area are very difficult to predict. So, we have looked at the technology and questions around the law. We've mentioned the future opportunities and challenges. Let's look at these in more detail. So let's look at potential benefits of autonomous vehicles. The following is a list of commonly perceived benefits of autonomous cars. There may be increased road capacity and reduced traffic congestion due to reduced need for safety gaps and the ability to better manage traffic flow. There could be potentially a higher speed limit. All constraints on the driver's ability or state could be removed. A fully autonomous driverless car could have passengers which are blind, distracted, intoxicated, underage, overage, or otherwise impaired. The need for redundant passengers could be eliminated. There could be a reduction in the need for traffic police. It may be possible to reduce physical road signage. Humans could be relieved from driving and navigation tasks completely. There could be improved parking capacity. Cars could drop off passengers, park away from where space is not scarce, and return as needed to pick them up. It is likely that intrinsically safe vehicles will have less collisions, leading to lighter, more sustainable materials being used in their manufacture. The following is a list of commonly perceived challenges and disadvantages of autonomous cars. There will be complex and potentially hazardous interplay between different levels of automation using the same road space. Moral, ethical choices may be too difficult to program into vehicle intelligence, where it's forced to choose between multiple courses of action, all of which cause harm. Overall intelligence software of vehicle sensor system reliability may be difficult to achieve. A car's computer could potentially be compromised, as could a communication system between cars. As they rely on increasing automation, the technology may result in drivers being inexperienced to deal with complex situations. Driverless cars could potentially be used by terrorists or other criminals. There may be a loss of driving-related jobs. The cost of vehicles may increase. The reputational risk for motor manufacturers and their suppliers could be too high. The technology could accelerate shared ownership of cars and a reduction in individual ownership models, disincentivizing vehicle manufacturers. The following is a list of recent predictions regarding the arrival of autonomous vehicles. Major automobile manufacturers and technology companies have made numerous predictions for the development of autonomous car technology in the near future. The new Volvo XC90 will feature adaptive cruise control with queue assist, which will automatically follow the vehicle ahead in queues. The Institute of Electrical and Electronics Engineers, the IEEE, have estimated that up to 75% of all vehicles will be autonomous. Tesla has just launched its autopilot feature with its 6.1 over-the-air firmware update, and more promised in the 7.0 firmware update planned for mid-2015. Estimates by Morgan Stanley indicate that autonomous cars could save the United States $1.3 trillion annually through lower fuel consumption, $169 billion, reduced crash costs, $488 billion, and productivity increases, $645 billion. KPMG LLP and the Center for Automotive Research, CAR, predict new business models and improvements in productivity and energy efficiency. So let's look at the opportunities and threats for insurers. Opportunities. There may be new channel customers, such as manufacturers and car share programs, new ancillary services such as navigation, safety, emergency vehicle maintenance, new risk products such as cyber risk and microinsurance, and commercial applications of data collected from the vehicles. And threats. These may be an increase in severity of claims arising out of collisions, increased risk of cybersecurity and data protection compromise, a reduction in overall losses, hence reduction in insurance premiums, increased risk sharing and pooling by manufacturers leading to a review of terms and conditions of trading, more complex levels of regulation in differing jurisdictions, a need for common infrastructure architecture of support systems, and the role of local and national government in supporting and adopting these in conjunction with private sector suppliers. Now, Thatcher has also looked at future modelling and has undertaken some very preliminary modelling, and this shows the impact of the emerging autonomous technologies on risk and the changing nature of this. This is shown in this diagram. The model shows a very significant reduction in personal risk over the next 30 years. In this model, a halving of personal premium could take place in the next 15 to 30 years with a simultaneous increase in product liability. We have to assume that the vehicle manufacturer will be liable if their products fail. Thatcher has also developed a preliminary model as follows to show the time taken for each new level of autonomous capability to penetrate the fleet, each level taking approximately 15 years to achieve 100% of new car sales. This model estimates that 100% new car sales of fully autonomous vehicles would not be until about 2040, and a further tail of fleet turnover with a further 10 to 15 years for the majority of the UK fleet to be fully autonomous. However, we must assume that in this period the government will act to incentivise the take-up of the technology as the mobility and safety benefits emerge. Also, as discussed at the beginning of this briefing, it's difficult to predict the market reaction to the emergence of this quite revolutionary mobility. A car which takes you where you want to go without you driving, this might be the most sought-after product since the smartphone. So in conclusion, the introduction of increasing levels of automation can be considered in two categories: the near future, next 10 years, and longer term, 2025 to 2040. These present different challenges. In the near term, there may be gradual introduction of automation leading to vehicles of all types sharing the same road space. The risks associated with this are therefore higher in the near term. It's likely that regulatory framework will adapt slowly to mirror the requirements on the ground. As the models above demonstrate, as vehicles become more fully automated, the risk of collisions diminish with the transference of risk from the driver to the vehicle itself and associated product liabilities. The way in which cars are used will likely change for significant parts of the road user population in the very long term, from individual ownership to shared ownership or car service schemes. The urban model may look very different to that on rural roads and differ particularly from country to country. For insurance, the current view that it is likely that liability will transition with the development of autonomous systems and then completely autonomous vehicles from the driver to the manufacturer, and that over time there will be a consequent reduction in personal insurance. Liability issues will have to include complex accidents in which infrastructure ownership, operator diligence and third-party actions are taken into account. The UK government is keen to get ahead, and there are significant opportunities for those businesses who react earliest. The revolution is coming. Be ready. I hope you found the briefing informative. More information on Thatcher Research's work on autonomous vehicle technology, in particular our promotion of autonomous emergency braking, can be found on our website at www.thatcham.org. If you have any further questions, please do not hesitate to email me at andrew.miller@thatcham.org. Thank you.